This course will start with a review of transmission lines. We'll start with transmission line equations. We'll solve this. Then we'll come up with the reflections in transmission lines. Then we'll determine the input impedance seen by a source in a transmission line, and we'll of course also determine the characteristic impedance and some secondary parameters of a transmission line. Thereafter, we'll develop the Smith chart and we'll apply it in determining the input impedance, and similar parameters in a transmission line. Then we'll apply pulses onto a transmission line and therefore come up with our time domain response. Thereafter, we look at partial differential equations in electromagnetism, and of course we will utilize Maxwell's equations to develop standard time periodic equations, which we'll then use to solve for waves propagating in space, both unbounded and then bounded waves. And of course, when we have bounded waves, we'll look at boundary conditions. We'll look at general plane wave propagation. We'll introduce Poynting's theorem that pertains now to the total power. Then we'll look at reflected waves. We'll look at both normal and oblique incidence. And we'll look at cases of total internal reflection and the occurrence of surface waves. Thereafter, we'll look at EMC, EMI, basic definitions. We'll look at some typical EMI and EMC examples, and of course a little bit about testing EMC, EMI. We now look at the expected outcomes for this course. On successful completion of the course, we expect the student to be able to analyze and solve simple electromagnetic field distribution problems relating to plane wave propagation, derive the primary electromagnetic relationships for plane wave and transmission line problem solving, analyze and solve simple transmission line problems relating frequency and time domain voltage and current distributions, analyze and solve simple transmission line matching problems, and understand the fundamental causes and remedies of EMI and EMC. The subsections for this module are shown below. The first subsection will be focusing on transmission lines, which will take about 4 weeks. And here we will cover transmission line equations, where we'll derive and solve the transmission line equations, and then we will determine the expressions for the characteristic impedance and the propagation constant for the line. Then we'll focus on different types of transmission line. We have a typical lossless line, which is an ideal line. Then we have a distortionless line. We have a low loss line. And for each of these, we'll determine the corresponding parameters. That is the characteristic impedance, and we'll also determine the propagation constant, out of which we'll be getting both the phase constant and the attenuation constant. Then we'll move on cylinder transmission lines. We will terminate the line in a certain load. And for this, we'll look at the corresponding input impedance seen by the source when you terminate the line in a certain load. And we'll look then at special cases of loads where we have an open circuit load, which means Z is infinite, or we'll have a short circuit load, in which case the termination is 0. We'll then determine the reflection coefficient along the line, and we'll also determine the standing wave ratio on the line. And as we determine the standing wave ratio pattern, we'll now ask ourselves what happens when along the line you have voltage maxima and minima. At those points, what is the corresponding input impedance? And then we will also determine the power delivered to the load, depending on whether the line is terminated in a matched load or on an unmatched load. Now, after that we'll look at the Smith chart. Now we'll derive the Smith chart from basics, and we'll use that to now determine how we can utilize the Smith chart as a tool. We'll determine the impedance as represented in the Smith chart, and based on that we'll determine the use of the Smith chart in impedance matching. How do we match, for example, match a load ZL to the characteristic impedance Z0 of the line? So we'll look at different types of impedance matching techniques. The main ones will be standard stub tuner, single stub tuner, and then we'll look at quarter wave transformer matching. Thereafter we'll look at transients on transmission lines. We'll look at multiple reflections on the line, and then we'll come up with what we call the bounce diagram. Now, for about 3 weeks in November up to early December, we'll be looking at wave propagation, and we will start with Maxwell's equations, and from Maxwell's equations we'll end up with our partial differential equations, which we will then solve for waves in unbounded media, which means waves in free space, and whatever the medium, it is unbounded, and from there we'll get the intrinsic impedance of the wave, and then we will also get the attenuation and constants and phase constants, attenuation and phase constants. Phase constant, remember, determines the delay of the wave, so that our phase velocity is determined by the phase constant. Now, we'll then look at plane wave propagating in lossless media, in low loss media, and in high loss media, like for example, good conductors are high loss media. So what happens when our waves propagate in these three media, the lossless and high loss media? Thereafter we'll look at bounded media, where we'll now determine reflection of plane waves when, for example, they encounter at an interface a different type of medium. So we'll calculate the reflection coefficient when we have normal incident, that is perpendicular, and then when we have oblique incidence. Once we are through with that, we'll look at module 5, which deals with EMI EMC. So we'll have basic definitions, then we'll briefly discuss testing of EMC and solving EMI problems. So that will then take us to the end of the semester. Thank you. As already perhaps alluded to, this being a different course because courses will be offered online, we will have tests largely and practicals, and therefore we have 4 tests scheduled on the dates given. We have test 1 on 8th October, test 2 on 29th October, test 3 on 12th November, and test number 4 on 17th of December. So students should start preparing early enough for these tests. Now all students are required to do practicals in EM theory, and there are 3 practicals listed there. Now each student will prepare pre-prac report, and after doing the practical, each student will present a post-prac report. These reports will be marked by the demonstrators. Now repeat students who have passed the practicals before will be allowed to apply for exemption from these practicals. Now let's look at the 3 practicals in detail. Now the first one, CE3, is entitled Electromagnetic Fields, and this particular one uses the slotted line, and in the slotted line we get what we call standing wave ratio measurements. When we have a load terminating a transmission line, depending on the type of load and how the load ZL relates to the characteristic impedance of the line, we can have a standing wave pattern along the line. Now, so we'll determine SWR, the standing wave ratio, for different types of loads. Thereafter, we'll also use the slotted line to determine the guide wavelength. Of course, the guide wavelength is different from the free space wavelength, because the guide wavelength is determined in this case in a guided wave. I'm sorry, in a waveguide, and we'll find that the guide wavelength and the free space wavelength are different. So we'll determine that at various frequencies of operation. Thereafter, we'll also determine the reflection coefficient. Any load that is different from the characteristic impedance of the line results in reflection of a portion of the transmitted signal backwards towards the transmitter. So we'll want to determine the reflection coefficient gamma. And finally, we'll try to determine the load impedance in each case, ZL. We can determine the load impedance by using the parameters of the slotted line. Now, in the second practical, which is CE4, is entitled Transmission Lines Investigation, we'll be looking at both twisted pair and coaxial lines, fairly standard transmission lines, and for each of these lines, we'll determine the following primary constants. We'll determine the resistance per unit length, the inductance per unit length, that's per meter, the capacitance per unit length, and the conductance per unit length. So we'll do this for each of the two lines, and we will use this to determine the characteristic impedance of the line. And then that is, so the characteristic impedance is the first primary constant, the first secondary constant. The second secondary constant, or the second secondary constant, is determined by looking at the propagation constant gamma. Now, gamma has two parts. The real part of gamma is the attenuation constant of the line, and the imaginary part is the phase constant of the line. So we'll be required to determine for each of those two lines the attenuation constant and the phase constant. And then we'll use these concepts to determine, for example, the length of a transmission line and the load terminating a transmission line. Now, finally, we'll be looking at CE5, and in CE5, we are looking at coupling. Coupling is a problem normally when you have lines of current carrying conductors adjacent to each other, or even in a PCB circuit, you have the risk of coupling, and we're looking at two types of coupling. There's inductive coupling, which in this case is magnetic, and then we'll also be looking at capacitive or E-field coupling. So those are the two main types of coupling we'll be looking at in CE5. Thank you. Now, as far as DP requirement is concerned, the handbook indicates to us that the DP requirement is performance of all practicals satisfactorily. This still stands. All students are required to perform the practicals satisfactorily. Otherwise, you will not obtain DP. Now, as far as assessment is concerned, we will not have an exam in this module. Instead, we will have 4 tests, and then we will have the 3 practicals. So the tests are allocated 15% of the marks each, and of course the 3 practicals are allocated a total of 40% of the mark. So we expect students to do all the practicals and do the 4 tests, and hopefully with that effort they'll be able to pass the module. Now, our standard reference for this module is the book by Sadiku, Elements of Electromagnetics, What I have here is second edition, but of course there are later editions. I think right now we have a third or fourth edition. Please utilize that book. It's a very good book. It has very good examples. Now those who want detailed physical analysis of some of the concepts of electromagnetic waves could look at the book by Loren and Coulson, a very, very useful book, initially published by W.H. Freeman. It is a book that maybe we have copies in the library, or you can get maybe even a copy online. And finally, there's the book by Guru and Hiziroglu, which used to be the main text before I introduced Sadiku. The beauty with the Guru and Hiziroglu is that it has also a lot of examples. It has a lot of worked examples, just like Elements of Electromagnetics by Sadiku. So please, one should be able to get a copy of Guru and Hiziroglu, maybe in the library or even online, maybe much earlier editions. And please utilize this. I wish you well with our current module. Thank you very much.